Hello everyone and welcome to Lesson 2, Properties of Periodic Functions. The goal for this lesson will be to explore properties of what are known as periodic functions. A periodic function is defined to be one whose graph repeats at regular intervals. The y values, which remember are the output, shows a repetitive pattern when the x values, which are the input, change by the same increment. We've already seen two examples of periodic functions that would be the sine and cosine functions respectively. They're shown in the graph below. In lesson 1, we only looked at the sine function from 0 to 360 degrees. That would be what I'm highlighting below. But what I'd like to stress over here is that there should be arrows at the end because the sine function goes forever left and right in all directions. And you'll see that that pattern which I've highlighted repeats again and again. The same can be said for the cosine function. In lesson 1, we only looked again from 0 to 360 degrees, which is being highlighted below. But in reality, this function extends forever in both directions, indicated by the arrows. So this is what we mean by a periodic function. That pattern repeats itself again and again over regular intervals. And now some terminology. First, the period of a periodic function is defined to be the change in the independent variable that produces or corresponds to one cycle. You can think of this as the minimum distance on the x-axis in which a portion of the graph repeats itself. Let's take a look at the sine function on the previous page and show you what the period looks like. So I want you to pay careful attention to that shape I've highlighted. That would be the minimum repeating pattern. If we were to extend the sine function, it would look something like this. Okay, I'm not quite drawing that to scale just to get it on the page. But what I'd really like to stress here is the period is the length of that repeating distance. So we can make a note of that below. Next up, we define the peak of a periodic function to be the maximum point on a graph. And similarly, we define the trough of a periodic function to be the minimum point on the graph. I just want to mention that because periodic functions repeat themselves, they're going to have many maxima and many minima. Compare that, for example, with a parabola, which only had one maximum or one minimum. In the picture that I'm sketching, we see that this parabola has one maximum value only at the vertex, but the sine function will achieve many maxima throughout its domain. Let's label these on the picture on the previous page. So you can pick one arbitrary point, let's say this one here, and that'll be one maximum. Of course, there are several maxima, and this point over here would be the location of a minimum. We call the location of a maximum a peak, and we call the location of a minimum a trough. So with that being said, in example 1, we're asked here to define the periods of the sine and cosine functions. So you should have discovered this in lesson 1, but let me reiterate here for clarity. Both the sine and cosine function have a period of 360 degrees. This means the graphs repeat every 360 degrees. Okay, let's try another example. This one is asking us to determine which of the following functions are periodic. In other words, which of the following functions show behavior that repeats at regular intervals. When you're doing a question like this, pick one feature of the graph. So in this one, I'm going to choose a maximum. Let's say this one right over here. And when does that maximum repeat again? There are several, but if I'm going left to right, the next maximum is at this location. So therefore, this pattern that I'm highlighting would be the minimum repeating pattern, which would be the period of the graph. And it's that shape that keeps repeating again and again. Therefore, this example would be a periodic function. If you look at the graph in the picture to the right, it appears to be periodic, but notice that we don't get the exact same pattern repeating. It kind of looks like a sine function, but do you see how the peak keeps getting higher and higher? So therefore, it's actually not periodic or non-periodic. In order for it to be periodic, the exact same shape would have to repeat over and over. And now some terminology, everyone. So we're going to look at something that's defined to be the equation of the axis. And I'll just make a note here. Sometimes it's also referred to as the axis of the curve. So you may see the other terminology used in the textbook, but not to worry here, it means the same thing. So what this is, it's defined to be the equation of the horizontal line that cuts the graph in half. In other words, it lies exactly halfway between the maximum and the minimum values. Let me just show you in a sketch here what this represents. So I'm just going to sketch a sine function or part of a sine function. So this would be our maximum, and our minimum is down here. And the line that cuts the function in half, which is exactly halfway between the maximum and minimum, would be your equation of the axis or axis of the curve. It's the dotted line that I'm sketching over here. So that would be the equation of the axis, or EOA for short. Now think about this quantitatively. If you're trying to find a formula for it, it literally lies halfway between the maximum and the minimum. So the way we find it is by taking an average. And the formula is shown here. Y equals the maximum value plus the minimum value divided by 2. So you're literally taking an average between the max and the min. And we're writing this as y equals because anytime you write the equation of a horizontal line, it's always y equals a number. So let's practice this in the next example. We're going to find the equation of the axis for each of the following. So let's start with the first picture. It looks like we have a maximum value of approximately 4 and a minimum value of 0. So we're looking at the y values on the graph. So using the formula to find the equation of the axis is as follows. Y equals the maximum value plus the minimum value. I'll just do max plus min for short, divided by 2. And now you just plug in the y value. So we have a max value of 4, a minimum value of 0, and we divide that by 2, and that'll give you an average of 2. And you could actually see this in the picture. Draw a horizontal line through y equals 2, and just verify that this actually is halfway between the maximum and the minimum. And I think from the graph it's pretty clear that it is. Let's do another one. In the second example here, it looks like we have a maximum value of 5, and it appears like we have a minimum value of -1. Sometimes you might need to use a ruler just to see where the line crosses the axis. It's a little trickier when you have negative numbers, but you'll see it still works out. So let's use the formula, y equals max plus min over 2. I'm just going to plug in the numbers just to save a bit of room here. So the maximum value is 5. The minimum value is -1. So be careful here. You're adding -1, which is equivalent to just subtracting 1. And 5 minus 1 over 2, that's 4 over 2, which gives you 2 once again. Just to verify that we didn't make a mistake, let's sketch a horizontal line through 2. And that looks just about right to me, halfway between the maximum and the minimum values. All right, a little bit more terminology. The next thing we have to talk about is something called the amplitude. The amplitude of a function is defined to be half the absolute value difference between the maximum and minimum values. You can also look at it like the vertical distance from the equation of the axis to the maximum or the minimum value. Let me just do a sketch here to show you what I mean. I'll just sketch a sine function once again. The equation of the axis will be halfway between the max and the min, so that's the dotted line for the equation of the axis. And the amplitude is defined to be the distance from the dotted line to the maximum or to the minimum. So in my picture, the amplitude would be the distance between the peak and the dotted line. And we just record it as a positive value. That's why I have the absolute value signs in the equation. Speaking of which, let's look at the equation. The amplitude, which we typically represent by A, is equal to the maximum value minus the minimum value. So it's similar to the equation of the axis, but rather than adding, we're subtracting. Also notice we have absolute value signs here. That means that whatever value we get, we make it positive, and then we divide by 2. So just a note here, the formula for the equation of the axis and the amplitude are similar. Please don't get them mixed up. Let's practice. This one is asking us for the amplitude of the following function. So looking at the picture, it appears like we have a maximum value of 6, and it looks like we have a minimum value of -4. And with that being said, we're ready to use the formula. So the amplitude is the absolute value of the maximum minus the minimum divided by 2. Plug in your values. The maximum is 6. The minimum is -4. So we're subtracting -4. And I'm going to make really big absolute value signs here just so we don't accidentally confuse it with a 1. Okay, divide that by 2, and here we go. Inside of the absolute value, you have 6 minus -4. That's going to give you 10. I'll still put my absolute value signs, but we don't need it because the absolute value of 10 is just 10, and 10 over 2 is 5. So we have an amplitude of 5. And let me just convince you that this really is the amplitude. I know this wasn't part of the question, but let's find the equation of the axis. So remember, that's y equals max plus min divided by 2. All right, the maximum is 6. We add -4 or subtract 4 and divide by 2. 6 minus 4 over 2 gives us 1. So our equation of the axis passes through 1. I'm going to sketch that in the graph. And the amplitude would be the distance from the dotted line to the maximum. So just verify. is there a distance of 5 between the maximum and the dotted line? And you can just count on the graph, and yes, indeed, there are 5 squares between those 2 points. It's also the distance from the dotted line to a minimum. But remember, the amplitude is always positive. We're just counting the distance between the 2 points. All right, and I believe that's pretty much the lesson. So we're just going to do a couple more examples now to practice. And we actually have a very interesting one in example 5. This would be more of a thinking question. So let's take a look. We have a bicycle wheel with a diameter of 80 centimeters. Imagine that a pebble got caught in one of the grooves, and if the wheel can make one full turn every half a second, we're going to draw a graph that shows the pebble's height above the ground for the next 2 seconds. For simplicity, we're going to assume that the clock starts at the moment the pebble gets stuck. Okay, so with that being said, we have to picture this a little bit. So we have a bicycle wheel on the ground. And the pebble gets stuck somewhere. So just to make it easy over here, let's put the pebble maybe at the top. At the top of the wheel, the pebble is a certain distance above the ground. And that distance happens to be the diameter of the wheel. And that was given to us. The bicycle wheel has a diameter of 80 centimeters. So at this location, the pebble is 80 centimeters above the ground. Let's say the bike is going left to right, then you can imagine that the bicycle wheel will rotate clockwise like so. And you can imagine that as the bicycle wheel rotates, the pebble will be at various heights. Like it'll be at this location, then this location, then this location. And basically, as time goes on, the pebble's height above the ground keeps changing. But I'd like you to recognize that after the wheel rotates one full turn, the pebble is back to being 80 centimeters above the ground. So this is actually a periodic function. So we're just going to make a sketch of what the height of the pebble looks like as a function of time. But one piece of information we need is how long does it take the pebble to go through one turn? And we actually know that. The pebble makes one full turn every 0.5 seconds. And that would be the periodic nature of this function. So every half a second, the pebble is back to where it started. So let's make a sketch. On the x-axis, we'll have time. That would be the independent variable. On the y-axis, we have height. That would be the dependent variable because the height of the pebble now depends on the time. And for simplicity, everyone, let's say we start when the pebble is at a maximum. In all honesty, the question didn't say. It's irrelevant here, though. What we're more interested in is the behavior. So what I know is that the maximum height of the pebble will never be more than 80 centimeters. That's going to be the highest point above the ground. But the lowest point of the pebble will be 0 centimeters. It's never going to be less than 0 meters above the ground. And this may not be obvious right away, but this actually resembles a cosine function. Let me show you what I mean. So I'll make the sketch first. Hopefully you remember this from lesson 1. When the pebble is 0 meters above the ground, it's halfway through one full cycle. And when it's back to 80 centimeters, it has made one full cycle. And remember, that occurs every 0.5 seconds. And we want to graph this for 2 seconds, so we basically have to do 4 of these cosine cycles. So we just repeat this pattern 3 more times. Okay, don't mind me, I have to extend my graph a little bit. I'm not doing this to scale, by the way, I'm just making a sketch, which is fine for a question like this. All right, so the maximum has to repeat every half a second, so that'll be 1 second, 1.5 seconds, and finally 2 seconds. Okay, everyone, so I hope that was clear, but the important thing here is to recognize that this is an example of periodic behavior because it repeats at regular intervals. And last but not least, we have a slight application question here. If the graph below represents tide cycles in the Bay of Fundy, let's use the graph to complete the table below. First question, what's the period of the graph? Well, to me this looks like a sine function, or maybe a cosine function, depending how you look at it. So I see a sine function hiding right over here. Be careful here, if we started at 5 meters above the ground, then we have to end at 5 meters above the ground. And that shape I highlighted would represent one cycle. And do you see how it repeats again? I'll just highlight it here for clarity. But you don't have to because we're just looking at one cycle for now. And how long does that cycle take to repeat? Well, you just look at the length of time between the 2 points, and it appears to be 12 hours on the x-axis. So the period here is 12 hours. Next up, the maximum value. Well, just pick any peak, and the location of that maximum appears to be 9 meters above the ground, so 9 meters. And the minimum, just pick any trough or minimum. It looks like it's 1 meter above the ground, so I'm just looking at the y values. And then the next two require us to answer amplitude and equation of axis. So the amplitude would be the absolute value of max minus min over 2, so that would be 9 minus 1 all over 2. That's just 8 over 2, which is 4. And the equation of the axis would be max plus min over 2. So that's 10 over 2, which is 5. And just to make it clear, we'll sketch the equation of the axis on the graph. And the distance from the dotted line to the maximum is your amplitude. And if you just count the units, 1, 2, 3, 4, it's 4 meters, which is consistent with what we've calculated. And that wraps up lesson number 2. Please try the following questions from the textbook for additional practice. Any questions, don't hesitate to let me know. Thanks for watching, and I'll see you in the next video.